Hi everyone. Here's a second icebox example problem. When 1.0 moles of ammonia gas is injected into a 0.50 liter flask, it decomposes into its elements. At equilibrium, 0.30 moles of hydrogen gas is present. Calculate the equilibrium constant. The first thing to highlight is that this is an icebox question. It describes an initial setup, some implied change before arriving at equilibrium. The initial setup and the equilibrium situation are in two different sentences. We have this telltale phrase, gas is injected into a flask. Then we have a new sentence that starts with at equilibrium. It was like this, and then we arrived at equilibrium. It's an icebox question. This says ammonia gas decomposes into its elements. We need to come up with the chemical reaction. Turns out to be two ammonias in equilibrium with 1 mole of nitrogen gas and 3 moles of hydrogen gas. A balanced chemical reaction with the double-headed arrow. It's an equilibrium system. Because it's an icebox question, I immediately set up my icebox, I, C, E. The values that I'm going to fill out the icebox with are molar concentrations. Here we have to be conscious. We have 1 mole of ammonia in a half a liter flask. So the concentration is 2 moles per liter. 2.0 moles per liter. That's the only set of numbers in the first sentence. We initially only had reactant. So the concentration of the nitrogen and the hydrogen here in the I line of the icebox are both going to be 0. Then, at equilibrium, 0.30 moles of hydrogen gas is present. 0.3 moles in half a liter. So that's the hydrogen gas here at 0.60 moles per liter. Our 0.3 divided by 0.5. There, the two products started at 0. They must have experienced positive change, and the reactant, the ammonia, underwent negative change. The hydrogen started at 0, ended at 0.6. That's a change of positive 0.60. The nitrogen is in a 1 to 3 ratio. 1 to 3 ratio with the hydrogen. So the change there is 1/3 as much. And 1/3 of 0.6 is 0.20. 0 plus 0.2 is 0.20 moles per liter. The ammonia had a 2 to 1 change versus the nitrogen, or a 2 to 3 ratio with the hydrogen. So it was 2/3 the change of the hydrogen, or double the change of the nitrogen, 0.4. And then 2 subtract 0.4 is 1.60 moles per liter. Once we have the icebox filled in, we can set up our equilibrium law expression. Here, the equilibrium constant Kc is equal to the concentration of the nitrogen multiplied by the concentration of the hydrogen cubed, because it's balanced with the 3. So in the equilibrium law, the hydrogen concentration is getting cubed. This is over the concentration of the ammonia gas squared. We can now substitute our equilibrium concentrations into the equilibrium law. The nitrogen was 0.2. The hydrogen was 0.6, 0.60. We're going to cube that. It's over the concentration of the ammonia. It's over there. 1.60. That's going to be squared. We need to be conscious of how we punch this into our calculators. We want to make sure we arrive at the right answer if we made it this far. I'm calculating away. 0.2 times 0.6 cubed divided by 1.6 squared. End up at 0.016875. We have a raw answer. We need to go back and consider our significant digits. The three values in the question all have two significant digits, so we want our final answer to have the same number. Turns out to be 0.017. This is the equilibrium constant, does not have units, so we made it to the end. This is an icebox question because it describes an initial setup that's allowed to change before eventually arriving at equilibrium. This style has the information distributed across two sentences, where the first sentence has some key words that describe the initial setup, and the second sentence starts with this phrase, at equilibrium. We had to be careful to use the volume and the moles to determine the concentration, which we then put into our icebox. We have one side experiencing negative change, the other side positive change. The change here is proportional to the mole ratios. Once we have the equilibrium concentrations, we substitute them into the equilibrium law and solve. And I hope that helps.